So our group topic is material properties and structures. So now let's move on to our outline or what we'll speak in the presentation is this seven major topic, which is introduction to materials, atomic structures and bonding, crystal structures, measurements and characterization method, common semiconductor material, how structures affect electricals and property, and the last is the summary or the conclusions. So let's move out to the first heading is introduction about material. Materials are properties that in this scientists material properties which focus on how these properties are influenced by material compositions and structures, and they are really very useful, and they have four major types of material, which is metals, polymers, uh, ceramic ceramic and composites and all. And metals in briefly known for the strength and conductivities, and polymers. These are large molecules made up of from repeating units. And third is ceramics, inorganic or non-metallic materials that are typically hard and brittle. And fourth is composites. These materials combine two or more constituent materials with significant differences. And the next slide is how material structures matters in electronics devices. So, in briefly, I would like to say that it is a this the structures of materials of electronic devices is crucial because it determines the material ability to conduct or insulate electricity, and this conductivity is essential for the operations of electronic components like transistors and diode, which are the building blocks of modern electronics. And additionally, the arrangement of atoms and ions in material structures affects the electrical properties in which the vital for the functioning of devices like microprocessors and memory chips. And let's move on to the next slide is and this is again about the materials property, and the next slide again is atomic structures and energy level. So mostly energy level are distinct states that electronics can occupy within an atoms. These levels arise from the quantizations of energy, meaning electrons can only exist in specific energy state and not in between. And principle of energy level sub level. First, there are two principles. First is principal energy level. Elect I'll briefly explain. It is electrons are arranged in principal energy levels, which are often referred to as shells. Let's, for example, n is equal to 1 can hold 2 electrons, n is equal to 2 can hold 8 electrons, and sub level. Each principal energy level contains sub-level as SPDF that further define the arrangement of electrons. And the next slide, I would like Jirayu to explain it.
Uh, Bonding determines how electrons behave inside a material, which directly affects conductivity. The type of atomic bond controls how easily electrons can move. Metallic bonds have free or decolorized electrons, so metals like copper and aluminum conduct electricity very well. Covalent bonds, like in silicon and germanium, have shared electrons. These electrons are more localized, so the conductivity is moderate, but we can control it through temperature or doping. Ionic bonds, such as in sodium chloride, have electrons tightly bound to ions, which makes them very poor conductors. So overall, the bonding type sets the material's band gap and mobility, which is why it's important for electronic devices. Go to the next slide. Here you can see how each bond type influence electron movement. In metallic bonds, electrons move freely, giving metals high conductivity. In covalent materials, electrons need enough energy to cross the band gap, which is why semiconductors become more conductive when heated or doped. And ionic materials only allow ions, not electrons, to move, so they act as insulator or the or dielectrics in devices. These differences show how metals are used for wiring, semiconductors for chips, and ionic materials for insulation. Go to the next slide. So now moving on to crystal structure, crystalline materials have a very ordered atomic arrangement which gives electrons a clear path and result in high mobility. Amorphous materials have random atomic arrangements, so electrons scatter more and mobility is lower. That's why crystalline silicon use, is used for chips, while amorphous silicon is used in cheaper applications like display and solar panels. Go to the next slide. Uh, for silicon crystalline in a diamond cubic lattice, where each atom form four covalent bonds in a tetrahedral shape. This strong and stable structure gives silicon its moderate band gap and allows high carrier mobility. Because of this, silicon becomes ideal for transistor and integrated circuits, and the better the crystal quality, meaning fewer defects or dislocations, the better the device performance.
Okay. Next is crystal quality, charge mobility. Crystal quality describes how perfect and well-ordered the atomic lattice is. High-quality single crystal have very few defects, allowing electrons to move smoothly. With high mobility, which leads to faster device operation. In contrast, polycrystalline or amorphous material contain many defects, such as gain boundary or vacancy. These defects scatter charge carrier, reduce mobility, and increase electrical resistance. Since mobility directly affects device speed and power efficiency, semiconductor malfunctioning focus on improving crystal quality and minimize the defect. Next is crystal measurement. Crystal measurement ensure that a wafer has the correct orientation and minimal defect. Orientation affect electrical behavior and etching, while defect detection ensure the wafer is suitable for reliable device fabrication. The goal are to verify that buffer meets specifications such as alignment, thickness, and fatness to ensure long-term reliability and to maintain quality control during wafer selection. Common techniques include XRD for orientation and crystallinity, optical microscopy for surface defect, AFM for nanoscale roughness, SEM for structural detail, and S-pit counting for defect density. So next is X-ray diffraction. XRD is used to identify the crystal structure of a material such as FCC, BCC, or diamond Q. It also determines lattice parameter by measuring the spacing between atomic paint from abstraction peak. XRD can measure crystal orientation, which is important for IC fabrication. The technique is based on back law, where constructive interference occur when X-ray defect from crystal paint at specific angle, producing diffraction peak. Each peak in an XRD pattern corresponds to a particular crystal paint, allowing identification of material fate. Peak broadening indicate defect or small crystallized size, while peak shift reveals stain. Lattice parameters are derived from the two peak position. Next.
Well, I will be talking about the microscope. The first one is the scanning electron microscope. It is basically a powerful microscope that can zoom onto surfaces and get high resolution images which can be clearly seen by the human eye. And with the image, you can examine properties such as grain boundaries, topography, and surface morphology, and also inspect other things like surface defects, thin films, and grain size. And it works by using a focused electron beam instead of light to scan the sample surface. And like what happened is that the electrons they come out and like they interact with the surface. When they interact with the surface, they produce secondary electrons, which then produce more backscatter electrons, which turns into the signal that can be used to create the high resolution images. And from there, you can detect more things like cracks, voids, or surface defects in wafers or thin films. And you can also measure the grain size and boundaries in metal or semiconductors using the SEM. And also study the surface roughness and coatings. And this is important for things like material characterization, quality control, and failure analysis. Yes. Next slide. Uh, the transmission electron microscope is basically like the scanning electron microscope, but instead of surfaces, this is used for for um for the internal structure. And it basically works as the earlier microscope, where they shoot the electron beam through the ultra thin specimen. And like from there, you can look at the crystal defects, you can look at the dislocations, the vacancies. It's basically the same thing. Next slide. And what do those measurements tell us? They tell us how perfect the crystal is. They tell they, they tell us that the defects and imperfections, and they tell us that the orientation, and they tell us the metrics. Next slide.
So the next slide, I would like to talk about the common semiconductor in materials. So let's first look at the materials power industry. We focus on the main three players, which is silicon dioxide, and gallium arsenide. So let's talk about the silicon. Silicon is the dominant material in microelectronics and integrated circuit. It is the crystal structure diamond cube Its advantage is well understand fabrication process, high quality wafers, but mature technology. So the application is based on transistors, ICs, ME, MEMS solar cells. So then next we are going to talk about silicon dioxide. This it acts as an essential insulator. It protects the silicon surface and control current from flowing into the transistors. So that's based on its function. So its application is most device, capacitor, thin insulator. So moving to the next, which is the third one, gallium arsenide. So gallium arsenide is for high-speed application. We use this in a higher electron mobility than silicon, making it perfect for high frequencies electrons and optoelectronics like LEDs. So that is the application. Its application is high-speed electronics, LED laser diodes, and next slide, please. So, however, the materials alone isn't enough. The internal structure is what dictates performance. So let's talk about the defects and dislocation. So defect is like imperfection in the crystal lattice act like roadblock. They scatter electrons, increasing resistance and heat, which we want to avoid. So moving to the next one, which is gain. So the gain is present in polycrystalline materials, act as barrier for carrier transport, reducing conductivity. In, impact depends on the gain size. So moving to the next, which is doping. Doping. This is how we take control by internationally adding impurities. We determine if the materials conduct via electrons or what. So that's the doping. Examples, which is N-type, P-type regions in MOSFET. So moving to the next, which is strength and interface. So strength, we also use strength engineering by physical stretching the lattice. We can actually open up pathways for electrons to move faster, boosting the device speed. So next slide. So then the practical design consideration. Let's start with the first part, which is material selection. When moving to practical design, like engineers focus on many of these three. So the material section, we must match the materials to the need. We choose silicon for rose and logic or gallium arsenide for display. So mostly example, they are high-speed transistor, high mobility. Then the example which I've mentioned earlier. So the second one is early characterization. Perform wafer acceptance testing characterization before the fabrication. So moving to the next one, which is processing control. So processing control, finally, we must strictly control temperature and cleanliness. Even tiny contaminants during the process can ruin the crystal structure. It can kill the device. So we have to control the controlling processing control. Example, the thermal oxidation or thin film deposition must contain clean control environment, which I mentioned earlier. Next slide, please. So in summary, we have mentioned the material structure, which is atomic arrangement, crystal lattice, fundamentally determines the electronic properties. Then the next one, which was the bonding type and lattice structure, define the band structure, determining whether a material behaves as a conductor, semiconductor, or insulator. The next one, which is characterization tools such as FRD, SEM, and TEM, are essential to verify crystal quality before device fabrication. The next one, which is high crystal quality combined with controlled doping and processing, leads to better device performances. So this is the end of the presentation. Thank you once again for listening. Then the next slide, which is the reference and further reason. These are the reference from the textbook and online sources where we get all the stuff that are in this slide. Then the next slide is the responsibility of each prospective member in the group. Thank you once again for listening.